Okay, then let's get started. So good morning, everyone, and welcome to another Northwest Database Society talk. And this is part of the Microsoft Database Talk series. And today we're super happy to have with us Professor Tim Kraska. Tim is a professor at MIT, and he does really cool work on kind of using different machine learning techniques to make database systems better. And today he will talk about kind of a way to build instance optimized data systems. So thank you, Tim, for being with us today.
Thanks, Magda. Yeah, thanks again for having me here. So let's directly jump in. So my research normally is focused either on building systems to make machine learning easier to use, or nowadays I'm mainly focused on machine learning for systems. So for the first category, for data systems for AI, we built this project called Northstar, which actually is now a company called Imlic. Unfortunately, I don't have any time to talk about that, but if you are interested, you should definitely go to our webpage and check out the video. In this talk, I will mainly focus on our more recent work on how to leverage machine learning and other techniques to improve systems. So what's the whole motivation behind that? We all have seen this plot already that Moore's law is ending, and probably also have seen a plot similar to this, which is just saying that data is increasing at a never-ending pace. And so the question becomes, how can we deal with the onslaught of data while the hardware is not improving at the same speed anymore? And one way to do that might be specialization. And we already see specialization happening a lot in the hardware space, from GPUs, TPUs, FPGAs, and co. But is there also an opportunity for systems? And actually, specializing systems to get better performance for certain types of workloads is not uncommon. In fact, most databases we deal with nowadays are already specialized as they come. So we have operational databases which are specialized for OLTP, like HStore, Oracle, and co. We have analytics database system, which normally use a different type of storage format, and they are optimized for long-running queries like Snowflake and Redshift and others. There are streaming databases and so on. So we already see this specialization happening. However, the question is, can we specialize them even more? Can we tailor a system entirely to a given workload and data distribution to get even better performance out of them?
Alexa, stop.
Okay, so there are different ways to achieve what we call now instance optimization, so that we tailor a system to an instance of a problem for a particular user, for a particular workload. And the first thing we could do is just it's essentially tune the knobs and parameters the system has. And this is becoming mainstream now. So there are more and more systems out there which allow self-tuning. So there are components which tune all the knobs a system might have for the observed workload and data distribution. Examples include SQL Server, Microsoft SQL Server, who have been working on that for a long time. Amazon Redshift announces automatic table optimization. Oracle has their self-driving database systems. So there are a whole bunch of these self-tuning systems coming out, which help to tune a bunch of knobs a database provides. We at DSAIL are not focused on this first part. Rather, we want to go beyond that, and we are looking particularly into if we can create learned components. So that means we take a component of a database and try to hyper-optimize it using often machine learning techniques to get even more performance. So essentially, you're building a component, let's say indexing, query optimization, one of them, in a way that you consider learning from the start and that itself adjusts to a given workload and data distribution. And there's some earlier adaptation of these techniques. For example, there's a very recent integration of learned index structures into Google Bigtable. However, what we are really after is what we call instance optimized systems. And that is just be able to completely self-adjust an entire system, not just a single component of a database for a given workload and data distribution. And we are still very early with that effort. So in the end, this comes back to take all the learned components we are currently working on and try to figure out how we can bring them all together and maybe if there's synergy effects between the different components. So instance optimization, often we use machine learning techniques, but like in general, like instance optimization, machine learning is just one of the techniques you can use. Often just like plain good optimization techniques, linear programming, and so on can help to achieve the same goal. And in our opinion, you should use what makes sense in every single situation. So machine learning is just like one of the things in our toolbox. So the whole area right now is very, very active. There are a whole bunch of papers appearing almost on a weekly basis, which try to address like one component of a system using some ML enhanced method. Here's just like a brief like overview of some of the work like on components we also have been working on, but there are many, many more papers by now. Like this is getting too quickly outdated. So I'm only saying that's just like, yeah, this whole idea of like ML enhanced database components, system components, or algorithms and data structures is very, very active right now. And a lot of people are jumping on it. So for this talk, I have 3 goals. On one hand, I would love to provide a quick progress report on learned index structures. So that's a paper we wrote like 2.5 years back. About like how to leverage machine learning, particularly for indexing, hash maps, and Bloom filters to get better performance or smaller size. Then I would love to give you a very brief summary of some of the other components we worked on. And then in the end, show you early results of our SageDB system. So depending on time and depending on the numbers of questions, I might have to skip over many of them, but at least I can still give you like an indication where hopefully the state of the art currently is with ML enhanced algorithms, data structures, and components. Does it sound good? Okay, so let me start with the first one. So like in 2018, we published a paper showing that you can replace index structures like B trees using models. And on one hand, we got like extremely like enthusiastic feedback about it, that like machine learning just ate algorithms. That's the best thing I've seen in a long time. Essentially, that's the best thing since sliced bread. On the other hand, we also got a bunch of other reactions to it and complaints that we maybe have not compared against like the certain type of B tree tunings which have been proposed in the past, that there are other data structures out there which were not part of the evaluation, that there are a whole bunch of problems regarding theoretical guarantees, that no updates are supported, and so on. And I have to say many of these critics points were actually valid, because this was just like a very initial type of work, just showing that like, yeah, there might be something here, but there's still a lot of work to be done. Luckily, people started working on it, not just us, and many of the concerns which were raised like 2 years ago, they are by now actually already addressed. So what was the core idea behind the paper? It's actually surprisingly simple. So we saw that we have a B tree which takes a key and gives us a position, for example, either on disk or in memory. So why can we not replace this structure using a model? So we give them a key, it predicts where the data might be, and then we might do like some local correction, local search to actually find the data on disk or in memory. So the key point here is it gives you exactly the same guarantee. It's not like an approximate structure that might return the same result. It always gives you the same semantic guarantees as a B tree. If the key exists, it will be returned. Yeah. So to give you a very simple example of this idea, it's just like, let's assume I have this table of orders here. So I have some order data, which contains an order ID, a date, email address of the person of the customer, addresses, and so on. So let's assume for the moment, I want to always look up my orders by the order ID. And the order IDs in this case are essentially auto increments. So they start at 1000 and they are increment by 1 with every order. So on one hand, I could of course use a B tree for this particular case, just like put it in there, create a clustered index over them. And I can use the B tree to find a particular order ID. But if you just look at the order IDs and you know that they're auto increments, probably much easier would be that you do a direct offset calculation. So given ID minus 1000, you know exactly in this array of orders where the data is. And now the lookup performance is just like it's one addition, it's O of 1. It has a storage overhead of 1 integer. And if you compare that to a B tree, of course, it's much worse, right? Because for this particular case, looking up a key is trivial, given that we know that they're all auto increments and they start at 1000. So now let's assume we want instead index everything for date. This is a little bit more complicated because they are not like auto increments anymore. Rather, what we do in order to find it, we can build a CDF model over the distribution, which just like given a date item tells me how much probability mass I have below that date. And if I multiply that then with the total numbers of items I have, I get again an offset into the data like what I did before. This offset, depending on the quality of the model, might be like directly on spot or might be further away. So if the CDF model would be perfect, I would always get to exactly the record I'm looking for. If the CDF obviously is not perfect, I might have to do some local search around. And given that I know that all the data is sorted by the date, which is a requirement to support range requests, it's like relatively easy to do this correction. So again, this is not an approximate structure. It provides the same guarantees as a B tree because of the local search at the end, which guarantees if the key exists, you will find it. So far, so good. So what we did is we replaced now the B tree structure using a model which gives us a position estimate. So what types of models to use? In the end, whatever works, we just found that in many cases, what we call is an RMI, recursive model index, performs extremely well. The idea behind it is just like it's a mixture of expert models. So you train one model over the entire data distribution. Based on the model prediction, you pick another model, which then eventually might make the prediction estimate where it is in your data. So in the case that all these models might be linear regressions, the pseudocode here at the bottom shows you the whole inference code to make the prediction and then find eventually the key. So for linear models, this would be just 2 additions, 2 multiplications, 1 array lookup, and then of course at the end, the localized search. If you compare that with a B tree, which has a whole bunch of if statements and other things, this is extremely fast and hard to beat if you can like fit good models through your data distribution.
Interesting.
Thank you. Okay, so we did an early evaluation of that in the paper, and we show that like compared to other data structures for various data sets, we actually get pretty good performance. So what you see here in this experiment is that the y-axis is the index size, the x-axis is lookup performance, so where you want to be is the lower left. And the learned index structures performed like really well compared to other alternatives like FAST is a highly optimized ND data structure, lookup tables, fixed size B trees with interpolation search and so on. So all that should be like, if you hopefully have seen the paper or like some version of it, you might already know that. But when we published it, there were like a whole bunch of criticism which came out back then. And since then, we were working hard on addressing them, and not just us, there are many other people who helped us there. So one criticism was just like, oh, there's so many other data structures and B tree structures out there, you didn't compare against all of them. And obviously that's true because there are really a ton. There's no theoretical foundation, there's no update support yet. What I showed you so far is only for read-only workloads. And one other big topic was always, does it even matter? So you get a little bit smaller index sizes, normally only for clustered index. How much does it actually impact real-world workloads? Yeah. So for this first part, I will just quickly iterate over some of this criticism and where the state of the art is right now. So regarding other baselines, actually like TU Munich, like Thomas Neumann had a blog post there where you compared like the results from our papers with some like structures he just built on the fly. And so we decided to join forces in order to really to get to the bottom of it and see on how they compare against like different other variants, different optimizations, and just like also get another party in so that like there's no bias. So together with TU Munich, we did this like exhaustive benchmark study, which is going to appear this year in VLDB. And it shows that across like a wide range of use cases and data sets, it's just like the learned structures actually perform extremely well. As part of the study, we also included other learned structures by now, indexes like PGM or radix spline, which have been developed in the meantime. They are like a slightly different than the RMI approach, which I showed you earlier, just this like mixtures of models. Those are like actually trained bottom up and often use splines in order to fit the data. Overall, the result from the study is just like, yeah, they're holding up extremely well. And that's partially also explained by a paper Paolo from the University of Pisa did with the students around why are learned index structures so effective. And they showed that if you capture something about the underlying data distribution with high probability, actually the index size becomes much, much smaller. So there's like some theory now behind the results, thanks to Paolo and his co-authors. Another big question was just like, what about updates? And there has been a ton of work right now, like trying to improve or like extend learned index structures using updates methods. The one which is the easiest is often that you use a delta-based approach. So all the updates go in a delta, and then at some point you merge them with the read-only structure. But they are like also now in-place updates. For example, Alex. I think you heard about Alex a couple of weeks back by Jalin, even though I think he mainly focused on the multidimensional indexing, right? Okay, so the last one is just like, do smaller or faster read-only indexes even matter? And the criticism here was always like, yeah, if you look into the normal database execution, the time you spend in the index is normally very, very little compared to everything else, right? So it doesn't even matter that you make them faster or smaller. Faster, in some cases, they are limited. But one application is a nested loop join, where if every single like join key you have tests an index, of course, if the index is a little bit faster, it can matter. However, what might be surprising is that the size of the index can have a huge impact. And there are two papers out there right now. One is on integrating learned index structures into Google Bigtable, which shows that they can even get a 1.5x throughput increase and a 50% reduction in CPU usage using this index structure. And that's mainly because of the size. The reason for that being is that in a typical index structure they use for Bigtable, the index itself normally is contained in two levels. Two of them are on disk, and every single time you want to look something up, you actually have to fetch the second half of the index. The top one is normally in memory, but the second one you have to fetch, and that creates an additional disk I/O. And the moment you get rid of it, and you have a much smaller index, of course you save one I/O, and that helps you a lot. The other thing to mention here is like the CPU reduction you get, because like often the disk packages they have are compressed, and if you save a disk I/O and have a much smaller index, you do less decompression, which again helps your CPU utilization as well. Very similar, there's a paper by Wisconsin called WISCI, which shows on how you can integrate learned index structures into an LSM tree. Like RocksDB, and they show again throughput improvements mainly and latency improvements mainly again for the same reason that they save disk I/O. Right, so the size of the index can help a lot because suddenly you get much better caching behavior, and more of your actual data fits into main memory rather than that you use it for something else like the index itself. Okay, last but not least, like, are there any real limitations? And of course there are. The one thing which has to be pointed out is are duplicates. So in the moment your data contains a whole bunch of duplicates, the problem is often that the standard models we use in order to approximate the data don't work on it very well. So let's assume like you have a data distribution where a lot of the keys are just duplicated. What it actually creates in the distribution is some type of a step function. You have like, let's say the value 10 times, then the next value comes and suddenly jumps up from the position to the next one. And the step functions are just very, very hard to approximate using any continuous function. And normally through continuous functions, the space savings and everything else comes into place. Whereas like if you have the step functions, you're just storing the values when one step happens to the next is probably the better approach. And the storing the values when a step happens, that's essentially what a B tree does. Right? So the downside is essentially if you have a data set which consists of step function duplicates, it's very hard to use any of these like continuous functions to map it, and the space advantages are gone. So this is something to keep in mind. The trick would be now, let's figure out the right model for the right data distribution. In some cases, yeah, maybe you just want to store like the step points, which essentially makes it a B tree then. So just like for me, memorizing the steps is just another form of a model. As I mentioned earlier, this is a very active research area. There are tons of papers appearing with different extensions. Like one of the recent one I saw that they apply it to NVM memory, and I'm really excited about the results by Eric Lowe. They look pretty exciting to me and about the performance they are able to achieve. Okay, I will stop quickly here and take any questions before I move on to the next topic.
I have a quick question.
Sure.
So, I think I've asked you this before and you answered me, but I have a follow-up question. So if you apply a random hash function to the keys, then the random hash function will essentially distribute your unique keys, assuming it's your unique. It will distribute them very uniformly in the space of the random hash function. Then you have a trivial learned index, which is just a linear regression, which is the perfect approximation. And you told me that correctly, that will not support range queries. But still, has anyone studied the effect of applying a random hash function if you can give up range queries?
Yeah, so like I actually like normally I skip over the hash map part, but maybe for you this time I will cover it. Okay, so because I can skip actually over the next one. So normally I talk now about multidimensional index structures, but I know that you had Jalin recently here, so I will simply skip over that. And instead talk a little bit about hash maps. So in the original paper, we actually tried to show on how you potentially can improve the hash map performance. Right? So the idea was the following, like a hash map, as you just said, randomly assigns a key uniformly, or like actually you can use whatever pattern you want. It almost doesn't matter. You can use something which is queued as long as it's a random assignment. Right? So let's assume it just like randomly assigns uniform because it's the easiest to think of. The idea behind the LERD model was like, hey, can we potentially build a model which avoids conflicts? So spaces even more further out. And in the paper, actually, we show that this works, that like for the data sets we had, that we can build a model which reduces the numbers of conflicts you have. And interestingly, this is independent of what type of hash map function you use. So like this is an example of a separate chaining. So if you have a conflict, you just create a chain and you deep it in. And the hope is with the model, you reduce the numbers of conflicts you have, you spread it better out so that you have less slots, empty slots available. You can also use this with bucketing, and of course the effect goes a little bit down because with buckets you, for example, always have 2 slots available. So just like the chance that you actually create a conflict goes down, but still the effect is there. You can also do that with Cocoa hashing so that you have 2 hash functions and one of them might potentially be a model. So like the idea of using a model to reduce the numbers of conflicts is completely independent of the hash map structure you use. The key question becomes, when does it work that you can reduce the numbers of conflicts and when it doesn't? Right? And it actually comes down to how predictable is the spacing between the keys. So if I go back to the auto increment ID value, the spacing is perfect, right? Because I just increment every value. And so if I just learn this model, which covers that, which is just this offset computation, of course, I can avoid any left space and essentially the birthday paradox. The birthday paradox tells me that if I have n slots and n keys available, and I assign a random number to them and map them to the slots, just like I will get roughly 1/3 of conflicts. Right? So if I have now auto increments and I put a line through, like the model through it, the spacing between the keys is super predictable. I can better utilize it. Right? This is also true if I have some deletes in between, because essentially it just means that, like, yeah, it's not perfect anymore, predictable, but overall it's still a very predictable distribution. Right? On the other hand, when does it not work? And that is when the spacing between the keys is random. So if I randomly have keys sampled from some underlying distribution, take a uniform, normal, doesn't matter what it is, the spacing between the keys is not predictable. And essentially, like, I cannot do better, and I can show that, than normal hashing. And this is like the case for overfitting. It works if you're able to overfit to the underlying data. It doesn't work even when your model learns the underlying distribution. So if I have a model which learns the underlying distribution, I can still not be better than a normal hash function. Does that make sense?
Yes, thanks.
Yep, okay. So, and now you can actually try it out. You can say, like, okay, for separate chaining, if the slots are very predictable, we get the RMIs like our learned model compared to a hash function, you get an advantage. You also get an advantage if you use cuckoo hashing, right, for the same exact reason. Whereas, like, if I have a data samples from a uniform distribution, actually it's worse, mainly because the model adds some additional overhead and so on. Right? So this is like just an experiment to show what we know in analytical now. It's just like, it just depends on how predictable the spacing between the different keys are. Yeah. So in the end, if you think about what learned index structures do, is essentially they build order preserving hash function in many ways. It's just like nothing else, and that in a compact way compared to this, like there's this perfect hashing, an order preserving perfect hashing, but normally they require huge like model size, and they are not like that fast in inference. Whereas, like in many cases with this learned indexing approach, we get a much faster learned hash function, which is order preserving. But again, it all depends on the underlying distribution. Okay. Any additional questions for hashing? No, then I will move on to Bloom filters very quickly. So the idea behind Bloom filters is that given a key, normally a normal Bloom filter uses like hash functions and bits to just say, is this key in the set? And it says either maybe yes, so there might be false positives, but if the Bloom filter says no, it's a definite no, so there are no false negatives, right? So that's a nice property of a Bloom filter. One approach to leverage models to improve Bloom filters is, so let's assume the key has something inherent in it, which tells me if this key might be in the set or not. So what I can do is that I can ask a model, is this key in my set? And it's almost like it's a classifier. So it tells me maybe no, maybe yes, because there might be now false positives as well as false negatives. Right? So it's just like I treat it as a classification problem. But now in order to give the exact same guarantees, I can put all the keys afterwards, which say maybe no, through a Bloom filter to give exactly the same overall guarantees than the original Bloom filter. So essentially, if the model predicts, oh, this might be not in the set, I still need to check if it's really not in the set. So if the model is perfect, I don't need the second Bloom filter here on the right. If the model is imperfect, actually, I still need to do it to filter out all the false negatives. Yeah. So we showed that over a bunch of use cases or data sets we tried, we saw roughly 36% space improvement. Interestingly, now other people came in again and improved upon that idea. For example, Michael Mitzenmacher has this like sandwich-based approach where you first have a key, let it go through a Bloom filter, Then if it's a maybe yes, you put it through the model. And then again, you use the same approach what we have, which is just like filters out the final false negatives using another Bloom filter. So there's like one model surrounded by 2 Bloom filters, and he shows that overall this gives better theoretical guarantees. Actually, now together with Michael Mitzenmacher, we also have a follow-up paper which generalizes this idea again and creates a whole bunch of different areas to improve the space consumption even further. So we essentially, what our newest approach does is if you look here at the model, if the model gives you a probability of if it's in the set, this probability is actually not used really. It's just like if it's above a threshold, we assume it's in the set. If it's below a threshold, we assume it isn't. Now the newest approach takes the probability into account and leverages that further. So again, there's a bunch of follow-up work here. I unfortunately don't have much time to go into detail.
So Tim, one quick question. Is this going to be kind of similarly as for the hash functions and the hash data structures? The idea is that if there is something intrinsic about the keys that allows us to kind of learn that there is some higher probability that they will be in the set, then this technique will work. And if they're purely completely random, then this would not necessarily be better than a regular Bloom filter.
That's correct. Yeah.
Okay, thanks.
Yeah. So like the model needs to get something from the case. So like normally, for example, we tested always for malicious URLs. And apparently malicious URLs have some inherent structure which tells them they might be malicious, right? And so that's like, yeah, the model detects that. But the difference here is just like the previous models were often CDF functions. That model here doesn't have to be a CDF. This can be just like a classifier and whatever you want to use. Yeah. Okay, moving on to the second part. So a summary of some other learn components. Just like one, we have the learn query optimization, and we are working on that already for quite some time. The idea behind learn query optimizer is to create a feedback loop to improve the query optimizer over time, so that we have something which actually improves. So if you think about the traditional query optimizer, query comes in, gets passed, you put it through the traditional query optimizer, which is normally uses rules in a cost-based model. You get the query plan out, you execute it, and you get the result back. As you can see, if the query optimizer makes any mistake, there's no feedback loop. It's not improving on its own. Okay. So we did this first work, which we called NEO, which was an end-to-end like machine learning model based on reinforcement learning and tree convolutional networks, which created this feedback loop. So like we created a neural net, which did the query optimization for you and had everything factored in. It was really an end-to-end model. Right? The way we encoded the tree, we made sure that like always a solution comes out which is valid. So it wasn't possible that you get an invalid plan, but like in the end, it's just like really an end-to-end one. So the learned model learns the cardinalities as well as the cost model. So this worked actually pretty well. But there's a big downside of that approach. One is the training time. So it took like a long time to train. And even worse, with every column you add to the table, you had to actually retrain the entire model. And so whenever you have a schema change on how we encoded everything, we didn't get the benefits that you can just like easily warm start it. At least we haven't implemented it, but just like you had to always to do a long training again. The other problem with this approach is like the decisions are hard to understand. So we like talking to people who, for example, run Postgres, we always got like a bunch of pushback because the question is like, how can you trust the decision it make, and what about regressions? So we started to develop a second system, which we call BAO, which actually takes advantage of traditional query optimizers and creates a feedback loop in addition over the traditional optimizers you have. So how does BAO work is you have the traditional query optimizer, and then we create variants of that by providing hint sets. So essentially we take the traditional query optimizer and say, okay, now use the query optimizer, but never use nested loop joins. Use the query optimizer, but only consider merge joins, nothing else. And so by providing hints, you can turn off certain rules in the query optimizer and create a variant of a traditional query optimizer, right? Like certain features are just turned off. And now what we do is the query comes in, gets passed, and it puts in parallel through a bunch of query optimizers. And then we have a model which learns over time what hint set to use in which situation. So based on the query, it tries to figure out which of this like variants of the query optimizer it should use. Yeah. So the advantage here is that like you get a pretty good feedback if like a query comes in and it says like, okay, this query shouldn't use a nested loop join. Probably it's just like it's a hint that one of the cardinalities is completely off. The other thing is you can run this whole thing in an advisor mode, because like in the moment you have this, you can say like, okay, maybe I run that offline, and what it spits out is a bunch of hints for certain queries, and you can just add them manually. So you don't have to put it actually anymore in the online system like Neo. This can be a complete advisor. Or you can put it automatically, and it just automatically like does the right thing based on the model you have. So we experimented with that. And this is like the BAO performance on Redshift, SQL Server, Vertica, and DB2. So how that experiment worked, we took like a workload, in this case, it's a corporate, it's a data warehousing workload we got from a big corporation. IMDb is like probably the join order benchmark, and Stack Overflow is another workload we are having. What you see here are the different plots for like BAO, for example, on Redshift at the top left corner, with the cost of running the whole workload as well as the time it took. Comparing Redshift with BAO, the thing here is BAO is just the query optimizer. So we forced Redshift to use the query plans BAO produces. So it's like, it's not a different database system. It's just like replacing the Redshift optimizer with BAO, which uses internally their own Redshift traditional query optimizer. And what you see here is just like overall, we get like performance improvements anywhere between like, let's say 30% and 10%. Interestingly, also the cost is reduced, even though for BAO, it includes the cost for the GPU to train the entire model. And so overall, this is a pretty promising result. The results also hold true across different types of database systems for various types of like analytical workloads. There is a catch here, and that is like we only show you analytical workloads because for transactional processing workloads, how BAO works right now is like you have to put a query through different query optimizers at the same time. So if your queries are very short running, we add a bunch of overhead for the query compilation itself. Right? For analytical workloads, this apparently pays off. For OLTP workloads, this adds quite an additional overhead, and we are currently working on a new version which mitigates that problem so that like it's always beneficial regardless if you have an OLAP or OLTP workload. The last thing is just like the training time went way down. So here it compares BAO against Postgres and Neo. So this is like the entire time on how many queries you could finish. So higher means better. As you can see here, it's just like BAO almost from the start is much better than Postgres out of the box. Neo at some point, so Neo running on top of Postgres catches up eventually, and it is faster because Neo can do optimizations which we cannot achieve using these hint sets because we're always limited to the traditional optimizer. However, it takes a long time until it catches up. And that's the biggest advantage of BAO is like almost from the get-go, you have something that is runnable and provides really good performance. I will quickly stop here before I continue, and if you have any questions.
So I have a question. I think I missed it when you said, but where do you get the hints from? Because you're going to learn kind of to provide improvements, right? So in this case, right, you kind of, right, so do you learn the hints, or do you someone providing the hints?
So somebody has to come in and provide the hints, like how to create a variant. So this is like for every single traditional optimizer, we look into what hints the optimizer provides. and use like these hint sets as like a way to create a variant of the query optimizer. Like the most common one is probably turn off nested loop joins, right? It's just like, this is a hint almost every query optimizer has, because like, yeah, nested loop joins can really hurt you if you do the wrong cardinality estimate.
Right. But then, so then my question is, so let's say I have a traditional query optimizer and I have a hint that allows me to ask to remove the nested loop joins. So then in my training set, do you generate like example queries with the hint on and without the hint on, and then kind of see what and kind of learn from what happens?
Yeah, so that's one way to train the whole thing. What we actually do is like we treat this one as a bandit. So online, it picks one or the other and has this like exploration with exploitation phase. And that's like how it gains like the experience over time. So if you don't have the history available, but like what you just mentioned is one variant you could use also to train the whole network. 100% correct. So I also highly recommend that you actually invite Ryan Marcus. He did this whole work. It will soon appear. I say here VLDB, but I actually think it's Zigmod. I strongly recommend that you invite him. He gives an excellent talk, and he can also cover like some of the efforts we currently have ongoing into trying to put Bower in production. Okay, given the time, I will do it very quickly. So we recently looked into sorting as well and joins. I will only cover sorting here very, very quickly. So like this came up almost like in the moment we published the paper, somebody like we had this thought of like, can we use this like what those order preserving hash function to speed up sorting? So the core idea is like you have let's assume a bunch of unsorted integers, you put them through a CDF model, and if the CDF model would be perfect, you can place the item directly in the sorted position, right? And so you can achieve an O of n sorting algorithm very similar to radix without being necessarily constrained on the key domain size. Okay. So that's the core idea. And then like the first step, you put everything through the CDF model, and then there might be a second step where you have to do compaction depending on like how much space you over allocate and or if your model is like monotonic or not, right? If your model is monotonic, you don't even need to exchange any swaps. If you have a non-monotonic model like the ARM ICE normally, which I showed you in the beginning, are non-monotonic, you might have to do some corrections. Yeah. So we tried that out even with the perfect model. So like what we did is we took like all the auto increment integers, we shuffled them and then put them through a model which just does an offset calculation, right? So like the model was perfect for that particular case, and we still found that it's not faster. Right? So even with the perfect cheap model, which is just the offset calculation I showed you in the very beginning, the sorting wasn't faster than a highly tuned sorting algorithm like IPS4O. And the reason for that is that there are a lot of random memory accesses during the step one, like you map a key to any position in my memory, which causes a cache miss, and the cache misses in the end kill you, because like other sorting algorithms are highly cache optimized, and they avoid, even though they have higher overhead, but they avoid the randomness, the random memory access, and are much better because of that. The other one is just like in the moment your models are not perfect, you actually have conflicts and you need to deal with those conflicts. So based on that, we actually created a variant of it, an improved learned sorting algorithm which used buckets. So it is much more cache efficient. So instead of sorting, you get an item in, you predict directly the output position. What we do here is that we first get an item in and we predict just in which bucket it should go. And then it's just like a subdivision. And then the next step takes the bucket and makes it a smaller bucket and so on. And because of that, we get much better cache performance. And there are a bunch of like other small tricks we played. I don't have time into going into them. But with these like tricks, we actually show that for like certain data sets we have right now, we get actually excellent performance and up to 30% better sorting throughput than the next best algorithm we were able to find, which is IS4O. which has been highly tuned as well. We also improved 55% over radix sorts, mainly because like if you think about radix, it takes a piece of normally the key and does the sorting based on that. And then it takes the next piece, which is like takes longer than if you take the entire key into account and make a direct prediction. So it's like it's less sensitive to skew. Again, there's a downside, and this has mainly to do, as before, with duplicates. So if you're sorting a whole bunch of duplicates, we know that we are currently working on a version which gets as good as IS4O, so it's at least not worse. But like the algorithm we had here in Sigma 2020, if you would actually use a ton of duplicates, like the performance wouldn't be as great because the models don't work as good anymore. Make sense? Questions? Okay, with that, I will go over our latest effort, and that is now so far. I only showed you like different subcomponents a database system uses. The big question for us is just like, can we not combine them into an entire system? So I have this like architecture diagram here I took from like Stonebreakers and Hellerstein's book. And at some point I looked at each of these components and like was wondering like which ones have been already addressed using some kind of like instance optimization on ML based approach. And it turns out that like almost all of them, like I can at least name you one paper which creates an ML enhanced algorithm for them. So it's just like for all the different components, there has been a lot of work already. But still, what hasn't been done yet is like, how can we put them together to create an instance optimized system? So we started an effort called SageDB, which exactly tries to do that. First, we wanted to build a database system from scratch. We then decided actually against it because we thought like, okay, if we really would develop it from scratch, it will take us 7 years until we get something usable. And instead, we figured out a way on how to build an accelerator for Postgres. So the idea is that we like integrate into Postgres using a foreign data wrapper, which is a construct they have to be extendable. And then whatever uses our tables, which we support, and functions we support, it goes into our instance optimized substructure, which acts as an accelerator to speed up the processing. So we get the full feature like compliance to Postgres, but still hopefully for a large set of the queries, we can provide huge performance benefits. The overall design is on the right, like it contains the typical components you would expect, like obviously we need a query log. We have a path selection, which tells you like for every single query about where to get through. We integrate BAO for the query optimization. We have our own compiling execution engine. Tsunami Cortex will be our multi-dimensional storage layout. We built our own block-based storage structure. So the idea is to have like the same type of design of separating compute and storage like you find nowadays with Snowflake and other systems. And we also have like a store for partial materialization. So the idea here is that like if we see certain queries come over and over again, asking for the same type of aggregates, we will actually materialize them automatically. All this is managed using a component which we call Hurricane, which is like our global optimization across the whole like system and the different subcomponents. So the current status, yeah.
Sorry, before you move on and go too far, there's actually one quick question in the chat related to your previous part of the talk.
Mm-hmm.
The question is as follows. Is there any correctness and stableness guarantees for the sorting?
The correctness is there. So just like you get the sorted output of. The question is if you have a stable sort I don't think that we currently have a stable one. We have an in-place one. Right, does it answer the question?
So thank you. So if the person who has the question wants to follow up, just please raise your hand or add another question to the chat.
Sure.
Thank you.
So we have an in-place version. I'm actually trying to remember if it was also stable. I'm not 100% sure anymore. Like I have to look into the paper because we thought about making it stable, but I'm not 100% sure if we actually, if the latest version we published did it.
Great, thanks, Tim.
Okay. Okay, so for the SageDB architecture, so this is like the current status we have. The green components, we have a first version running. The orange ones we are currently working on. Actually, there's one change. Power is already integrated. So it's still a system under development. We actually hope that in 2 months we have a full end-to-end prototype running. But we do have some very initial results. This is like a workload called Bitcoin, which we got, and it shows like how SageDB performs against Postgres, like standard tuned and expert tuned, as well as like a commercial database system, also standard tuned and expert tuned. The difference between standard tuned and expert tuned is like standard tuning means, yeah, you do what's normally generally recommended. Expert tuning, you really look at every single query and you try to figure out if I can create like materialized results and other things on top of it. So as you can see here, if you do the expert tuning, normally the storage consumption on the right plot in red goes way up because you start to materialize a whole bunch of results up front. There's the blue lines show you the latency. And what we see right now is our current prototype. We already get like 8x improvement over the commercial analytics system, which runs in the same cloud environment. However, I also should mention here for these results, it's just like it's very early. Certain optimizations like the block layout optimization, automatic replication, encoding, and partial materialization are already enabled. But many others, like the learned query optimization, multidimensional indexes, partially materialized joins, or memory hierarchy optimizations are not yet. It looks pretty promising, but our goal is definitely to get like to the 2 order of magnitude performance improvements over a highly tuned expert system by just combining all these different optimization strategies. Okay, I would like to call out like all my students here because they clearly deserve all the credits. Andreas and Ryan will be also soon on the job market, so you should definitely look out for them. But like again, all of them are great. They helped, or they are driving all this research. So all the credits clearly belongs to them. On one other matter, we are organizing a new workshop at VLDB on like learning enhanced algorithms, data structures, and systems. The idea is actually not that you submit your unfinished work there. The idea is that the whole workshop should be like a type of a tutorial where people who work in that area present work they have already done so that everybody gets together and can get an overview of what's currently going on. Like this nomination for speaker side is still up. So if you want to nominate somebody, please do, and definitely attend the workshop if you have a chance at VLDB on August 16th. And with that, I'm more than happy to take more questions. Thank you.
Okay, yeah, thank you very much, Tim, for a great talk. So we have a few minutes for questions, especially from people who didn't have a chance to ask questions yet. Please feel free to just raise your hand and then we can take questions live.
Let me turn off my screen sharing here so that I can actually see you then. Okay.
You mentioned that for the one of the big shortcomings for the index prediction was a lot of duplicate indices or just general issues with duplicates, and you said that essentially what you kind of have is like a step function of distribution. I know that you can potentially get some better performance and stuff like that from a decision tree based algorithm, or maybe boosted trees would be a more realistic implementation. Has there been any research into that? And if you could speak to that for a second.
What do you mean by research into that?
I guess has it been like tried to use boosted trees to as an alternative to maybe like a regression or something like that in order to improve performance there?
Okay, I mean like a decision tree, like you can see a B tree node is nothing else than a decision tree node, right? True. It's just like has a big spanner. So what we did is like in the very early beginning that we actually allowed that a B tree node is one of the models.
I see.
And then you get like a hybrid one. So in an extreme case, it would actually like just become a B tree. And in the other extreme case, everything becomes like linear regression or other types of models. There's another approach, which is just like, for example, radix splines, what they do is like they fit splines through the data, and then they put like a radix-based structure on top. And these also tend to work a little bit better with duplicates, because the radix-based structure takes care of a lot of the duplicates values. So like these bottom-up approaches have a little bit less of a problem, particularly if they work with splines and a bounded error guarantee.
Cool, thanks.
Great, thanks. Next question from Alex. Please feel free to unmute yourself and you can ask the question.
Hello, I'm just interested in, like, since you choose the approach of foreign data wrapper, how much it will limit you in the future, like with joins and so on? Just like practical question.
We are still trying to fully figure that out. Apparently, it's just like it works better than we thought. So like joins, for example, don't seem to be a problem to be pushed down in the foreign data wrapper. But I mean, like the final verdict, I think, is still out. Eventually, this is like our starting point. My guess is like eventually at some point we will create our own front end, like meaning a SQL parser and co on top of it.
Thank you.
Okay, thank you. Next question from Josh. So please unmute yourself and you can ask the question.
Hi there. I was wondering if there are plans to extend this sort of AI everything approach to distributed systems, or if you see the majority of the upside here being limited to sort of small, medium data systems like Postgres.
So like actually what we are building now is distributed. So like it's just, we have a Postgres front end, but just like it's still underneath is a distributed system in the end. And it can run on different machines. So like we will expand that. I think it's actually the interesting part is this whole idea of learned index structures came actually up for like another project using RDMA. The idea was there, like if you have data stored on a different machine and you want to access the data using remote direct memory access, how do you figure out which memory region to read? And so we thought like maybe we can predict the memory region you should read rather than just like store like a dictionary on every single machine. Right? And so this was like kind of the starting point of everything, because we thought like, okay, the prediction, maybe we can use the model for that. So I'm like a strong believer in that larger systems and distributed database systems, or like distributed systems in general, can profit from it.
Great, thank you very much. So we're exactly on time. Thanks again so much, Tim, for the wonderful talk, and thanks everyone for joining us on this Monday morning, and have a good week, everyone. Bye.
Thanks, Magda. Thanks.